And as it was announced, I'm going to tell you about a crazy thing, which is an idea to build a clock that is not based on electronic shell transitions, but on a very peculiar transition inside an atomic nucleus. And it is a very specific atomic nucleus. It's Thorium-229. And I will tell you, just turned me off. That's very brute. Okay, good. Then I can also remove this pretty thing. Oh, I will just do this. Good. All right. And so I thought this, I heard that this is some kind of a training. I'm not sure if I'm a trainer, but if you have questions, please ask questions, because I've given this talk about 100 times. So I know what's in it. And if you just sit through it, it's kind of a waste of my time and your time. So whenever you think like I'm not clear, please interrupt me many times. And if I don't make it to the end, I'm not sorry, as long as you learn something. Good. So what I will tell you about is the idea of mixing something that is from nuclear physics and something that is more or less from atomic physics, which is laser spectroscopy. And I will tell you, first I will tell you that this is a stupid idea and impossible. And then I will tell you that it may be possible, maybe, in one very, very exceptional case, which is Thorium-229. And that's radioactive, and that's why we do it here, just to build the bridge to why we are at the Atom Institute and why we do this here and why I give this speech here to you now. Okay, good. And I will tell you that this might be a transition that could be used as a reference transition for an atomic clock, and it's actually interesting clock transition because it is very, very sensitive to fundamental forces and interactions more than any electronic shell transition. And that's the basic idea, is build a clock that is sensitive to fundamental interactions. We can actually build a really lousy clock and still be very, very, very much more sensitive than any electronic shell transition clock can ever be. And that's the kind of the motivation for that. And that's a very old story. So I think almost 45 years ago, somebody said that, hey, among all the nuclear transitions that there are, among all the gamma rays, there may be one that is so low that you could actually excite it with light in particular. Well, at that time, there wasn't even a laser. They said you could excite it with light, VUV light, ultraviolet light. And so since then, we are trying to build this clock. So I keep repeating the talk since 10 years now. But there is progress, and there's actually a lot of progress this year. And I will tell you a little bit about what we believe to know about this nuclear transition. And it's all very promising. So yeah, that's kind of the menu for this presentation today. As I said, please interrupt me anytime. I have breakpoints in the presentation where I show this thing again, so you can think like whether you have followed or whether you would like to ask a question at that point. Good. Okay, so let's start with this weird idea of doing something with a nucleus that we usually do with atoms. Okay, and so I don't have to recapture this. I give this presentation to a large variety of people, solid state physicists, cosmologists, and so on. So the introduction is very, very basic. And if you get bored, just yawn, and then I will speed up. Okay. Atomic physics, atomic shell transitions, Bohr, electrons moving on orbits, almost classically in this picture. Typical energy scales are electron volts, 1 to 10 electron volts. If you put more in, the electron will just rip off. That's called photo effect. And then you have bound transitions, which are usually on the electron volt level, in the optical range. Okay, and this is what we use for clocks. This is what we use for spectroscopy to find out what atoms are there, and all the quantum physics and atomic physics that's been developed since the 1990s is essentially in these discrete atomic levels. And you can build a lot of cool stuff with that. in particular clocks. Not have to convince you about the beauty and the aesthetics of clocks. Good. So now we zoom in on the atomic nucleus. You see a scale there. We zoom in by 4 orders of magnitude. That's the nucleus. Nucleus is also a quantum object. Many people don't appreciate that, but you can write down a Hamiltonian Schrödinger equation. There's protons interacting, there's neutrons, there's strong force interaction, there's Coulomb repulsion, and so on. If you could solve it, you could come up with a spectrum. And it would look kind of similar, apart from, I have a clicker that doesn't click, but it does point, I think. Apart from, apart from this M. M means mega. And that means that the energy scales here and here are usually differing by 6 orders of magnitude, maybe 5, okay? But it's a large difference. So that means the tools we have here, in particular laser excitation, no work here. Okay, and that's why usually atomic physics and nuclear physics are different departments. These people don't really speak to each other. Sometimes there's disliking. Anyways, it's usually separated fields, okay? Because you need to push in that kind of energy scales in order to play with the quantum levels of an atomic nucleus. Good. Now, yeah, that doesn't work right. Now, wouldn't it be cool if there was a way to transfer the fantastic stuff that we have on the atomic physics side, in particular, all these coherent Ramsey, all this cool stuff, to an atomic nucleus, and try to do the stuff that we do in the quantum world with nuclei? And I already told you, impossible, because of this M. We don't have MeV lasers, okay? Not yet. People are building very, very high energy, not very high power, but very high energy lasers. But they're not like tabletop yet, okay? So we have still, we're kind of confined to the optical, maybe the UV range, but that's about it. And that's on the scale, that's about 1 to 10 eV still, okay? We don't have MeV or KeV energy scales in lasers available, so no can do, okay? These are separate fields until you go down the periodic chart. And I don't mean the Mendeleev one, I mean the entire Karlsruhe all isotopes chart. And you look at, okay, what are really the energy levels? Are there low energy nuclear levels to be found? And yes, this is like the record lowest there are in the entire periodic chart as far as we know. Obviously, there are extremely short-lived isotopes that we don't know that well yet. These are all kind of long-lived, okay? So this one, my guinea pig here, Thorium-229, lives 8,000 years. That's enough for at least so I can do experiments before I retire. Okay, and you see this one here has a spectacularly low excited state, okay? It's almost electron energy range, okay? So if I translate this into wavelength, it's 150 nanometers. That's a nasty wavelength to build a laser, but it's still like maybe a factor of 4 or 5 to what we are used to, okay? So that's kind of maybe reachable. And I see this approximate sign here. I will tell you how little we actually know about this energy. It has to be there. But for a very, very long time, we actually didn't know where it is, because that's a theoretical prediction, and you can't detect this in traditional gamma ray spectroscopy. This is a photon in energy, okay? It's still a gamma ray because it comes from the nucleus, but in terms of energy, it's a photon. Second lowest is uranium-235, which is already a factor of 10 higher, okay? And then it goes even more complicated. Okay, but this one here, this one looks promising. Maybe we can do something with that one. And that's what we try here, right? Okay, so that's the story. Good. So what we would like to do is essentially consider the excited state of an atomic nucleus, and in a quantum sense, like a 2-level system, right? Ground state, first excited state. And now we look at some characteristics. This is actually not a dipole allowed transition. It's a magnetic dipole, but not electric dipole transition. And these usually have long lifetime. Okay, and that's good for clocks. You remember long lifetime, narrow line width? Good, we like that. Good. Long lifetime in this case means minutes to hours, okay? So it's an excited quantum state, which has quite a lot of energy, but lives for minutes to hours. I will reveal today it's 10 minutes. Very recently measured, okay? Yeah, great. So that's really like really narrow line width if you ever want to have a transition. So cool. Let's try to play with this in a sense of a two-level system. Good. So if you think about doing this, and that's what I thought when I started doing this, there are many reasons why you actually shouldn't venture into this field. Okay. The first thing I already said, this thorium-229 is radioactive. Okay. It has a lifetime of 8,000 years, and I made that sound as if that's a good thing, and it is a good thing because it's in what we do here, it's mildly active. Okay. People that work with really radioactive stuff, they say like, it's nothing. It's okay. 8,000 years still is considerably longer than the age of the universe, obviously. So if it had been created in the Big Bang, it's gone. That means there is nothing on this planet that isn't man-made. Okay, everything we have is left over from the Manhattan Project. There's about 35, 50 milligrams for research of this material on this planet. Okay. So when we speak about we do experiment with thorium-229 and people ask me, how much do you have? And I tell them 10 to the 80 particles. Okay. So that's the game we are playing. It's a really, really, really rare substance. There's very few labs on the planet that have access to that. And it's really, let's say, sought after. So if you know somebody, let me know. Okay. Good. Okay, so it's hard to have, and it's radioactive, so it's not easy. It's not easy to work with. Yeah. How was it made? It was made by it's a decay product of uranium-233. Uranium-233 alpha decays, spits out a helium core. 4 particles go lost, so it's 33 minus 4 is 229. And why is there uranium-233? 2 kilotons of that were produced in the framework of the Manhattan Project because it was an alternate material for unpleasant things. It's now stored in the basements of Oak Ridge, and sometimes you get access, sometimes you don't. It's bomb material, so it's kind of decay product of bomb material. Very old bomb material, because the lifetime of uranium-233 is really long. I think it's 10,000 years or even longer. Good. Okay, so it's difficult to have, and then there's the other thing is that it is an atom also, after all, right? I cannot do experiments with a nucleus. This thing will have electrons, and if I start to push in this kind of energy into an atom, I will start playing with the electronic shell. I will ionize, I will do all kinds of stuff. And I don't want that, because the reaction of the electronic shell will be so many orders of magnitudes more intense that I will not be able to speak to the nucleus. The electromagnetic wave will actually not reach the nucleus, okay? So I have to make sure that there's no electronic transitions nearby in this energy range, which means I have to work with an ion. Ideally, I will rip out 4 electrons. Then the thorium is like a radon, noble gas configuration, and that means there's no like low-lying electronic states that I can speak to. Okay, so I need to control the chemical state of my nucleus, atom nucleus compound, so that my electromagnetic wave speaks to the nucleus and not to the environment. Good. M1 transition means that the transition coupled to the magnetic component of electromagnetic wave, and we all know that that's a really weak coupling. Okay, so this is, well, it's like 2 sides of a coin. It's a long-lived narrow transition we like, but the consequence is that it really, really doesn't like to speak to dipole transitions, which we don't like because that makes it really, really hard to excite, okay? And so that means not only we need incredible high photon energy in our excitation laser, we also need a lot of photons, which makes it, yeah, this is why it hasn't been done yet. Good. And then obviously there is the task of actually building a laser at this transition wavelength. Okay, so all of this has sad faces and makes things difficult and lengthy and not a good project for, at that time, young person like me to venture in. But there's a few advantages. And one already said it's a super, super, super narrow transition, which is cool. But what's even cooler, because there is no lack of narrow transitions also in the atomic world, right? We all know, we always say, oh, this is such a great clock transition. And we all also know, well, actually, the performance of any clock is limited by the laser and not the transition. There is no need for narrow transition. There's no urgent need for narrow transitions, let's say, if you really want to improve the clocks. Good. But this transition has the appeal that it is inside an atomic nucleus, and the level structure is dominated by the energy scales that are living inside an atomic nucleus, which is high. That means to perturb these energy levels, I need orders of magnitude stronger forces. Turning this around means that if I apply an electric or magnetic field, these levels don't move. I can do really nasty environment, and still this transition will stay narrow, and it will still more or less where it is. More or less, obviously. There are effects of the outside world also on nuclear transitions, but they are orders of magnitude smaller. To give you a feeling, the ratio is essentially the ratio of the Bohr magneton to the nuclear magneton. Okay, so there's a damping factor, how external fields influence this transition, and this includes black body radiation and so forth. Okay, so it is a very robust transition, which is actually the more appealing fact. Apart from that, it is narrow. Okay, and as I said, you can do really nasty stuff to this atom and still hope to have a narrow reference clock transition. And for me, at least, coming from the atomic physics world, the worst thing you can do to a transition is put it in a solid state environment. But unfortunately, that's exactly what we do. So what we do in this building, and you will see this on Thursday, I think, is that we actually put these thorium, we freeze them into solid state crystals. Okay, so we build crystals, single crystals from melt, which are transparent to 8 electron volts, and we hold these, we sprinkle these thorium ions in there, in the 4+ state, and then try to do spectroscopy on a solid state target. All right. And that's nice, because if you think about ion traps or optical lattice traps, you need vacuum, you need to have a duty cycle, and so on. Just having a small crystal, I will show you one on Thursday, it looks like a sugar cube, is a practical advantage. Let's not speak about the laser system, which will be huge, but the clock will be small. Good. So that is the setting. There's one more thing, is high sensitivity to fine structure constant. I will go to the next, no, I will not go to the next slide. I will tell you about it here. So these levels here, these two here, they are a result of the interplay of the forces on energy scales happening inside the atomic nucleus. Okay, and as I said, because the atomic nucleus is small, everything is sitting very tightly on top of each other. That means if there is a change in these forces, in these energy scales, like Coulomb repulsion being a little bit larger on Thursdays than on Mondays, then this will have a dramatic effect on these energy levels, because they are differences in bound state. Yes. Yes. It's Lambdicke. It's so deep Lambdicke. It's the best ion trap you can ever build as a solid state device. There is second order Doppler will be a problem. Yes. Anyways, there will be, like, the crystal will have all kinds of effects. The presence of the fields of the crystal will shift the transition, but we hope it's a homogeneous shift. Nobody knows yet. So it's a precise, not accurate clock, if you want. So there's that effect. So yeah, and there are I mean, as I said, putting something into a solid state environment is really a violent thing. So there are broadenings, there are shifts, but it's on the kilohertz level maybe instead of gigahertz in electronic transitions. Good. Okay. Yeah. Right. So these transitions, what I'm trying to say, and I will come back to this in 2 slides. What I'm saying is that these energy levels, because they are both bound states of the atomic nucleus, which intrinsically the binding energies is really very large, are very sensitive to variations of the forces that dictate this energy, which is predominantly the Coulomb repulsion and the strong force interaction. Good. Yes. Question? No. Just, yeah. Absolutely. And I will show you at the end of the talk that we do this exactly. We do X-ray pumping to the second excited state, which is at 30 keV. Cool. All right, good. So this I don't have to show to you. This is for people that have no idea about clocks and what they do. So, but this you already know. There is a reference transition. There is a stable laser. I try to feedback my stable laser on a reference transition, and then there's a few parameters that dictate how well a clock can work, at least on paper. Then there's all kinds of like real life also strikes, but let's think about real life later. What are the defining quantities for the theoretical performance of a clock? Well, there's usually the quality factor, which tells you the higher the transition frequency, the better your clock will be if you keep a narrow line width. And that's probably, well, as I said, it's 150 nanometers. It's a quite high frequency. In terms of frequency, it's 2012 petahertz, okay? So that's a petahertz clock instead of a gigahertz clock in cesium. So we increase the ticking speed, and then there's the standard quantum limit, which is essentially a statistical argument, which means that there is a scaling with interrogation time, with averaging time, and number of samples, n. Okay, and when I say we put this into solid state and we have 10 to the 18 or 17 or something like that, then that is, if that is still a very large number compared to standard ion traps, which have how many atoms usually, or ions? One. How many atomic clocks do you know that have more than one ion? I think there's just 2 or 3 in the world, but they exist, but they're really rare. Usually you have n equals 1. You do an ion clock with one single ion, and you repeat, and average over 3 days until you actually reach the precision that you would like to have. Here, it's solid state still, right? It's rare, but it's solid state, means 10 to the 17, 10 to the 16 ions can be interrogated. So there's a significant boost in N here, okay? So that's why we believe could be a good clock transition. Good. One last argument, and then I'm done with the introduction, is what I already said is, again, I'm repeating this. So if you look at where does the level structure of a nucleus actually emerge from? Well, it's discrete bound states as in atomic physics, okay? Now, in atomic physics, binding energies and transition energies are almost the same. If a typical binding energy is on the order of maybe 10 eV. If I put in more, then I will ionize, okay? So that means there's very little difference between the energy it takes to rip out an electron and the energy it needs to excite. There's maybe a factor of 2, maybe a factor of 3, okay? Here, entirely different. So the energy difference here, I said, is a photon on the eV level. The binding energies are mega electron energies. Because these particles are sitting so tightly on top of each other, the binding energies, the attraction and the repulsion are so strong that the binding energies are mega electron volts, okay? Now, if there is a change in one of the main energy contributions, like Coulomb repulsion, then these mega electron volt energies would shift a tiny little bit, tiny on MeV scale, okay? And I'm probing energy difference between those. And because there's this ratio of this energy scale to MeV, there is this enhancement and sensitivity, okay? It's like if you want to measure the temperature dependence of a stick, well, you better take a long stick because the overall effect will be larger, okay? And that's what we do here. So this stick here is 6 orders of magnitude longer than what we will be able to measure, okay? Good. So that's the underlying motivation of doing this. Most people that are in this business are not so much interested in building the world's best clock. They're actually interested in using this as a detector for fundamental interactions. And there's all kinds of proposals how dark matter, dark energy affects the fundamental interactions, and so on and so on. Okay, so that's more a detector scheme than actually a clock. If it turns out to be a clock, we take it too, but good. So the cool thing about this transition is that if one of the fundamental constants would vary, these levels would drift apart. What would be really bad if they would like drift in parallel, then we wouldn't notice. But luckily, because of parity arguments, these two drift apart, and there's a sizable measurable effect that changes the transition energy or the transition frequency, if you want. How much is actually not known. So there's an enhancement factor. It's roughly the ratio of these energy scales, but how a change in any of the fundamental constants actually translates into a change in binding energies goes beyond current, well, is on the edge of what nuclear theorists can do, okay? And nuclear theorists are fighting, most of them are Russian, are fighting vividly, how to, I put this modest, right? Vividly about how strong the effect would be, whether it's 10 to the 3, 10 to the 4, 10 to the 5. This one isn't clear, and I think it will have to be measured because theory can only go that far. Good. So that's the underlying motivation. Build a clock, do spectroscopy on this nuclear state, and then do it again a year later and see if it has changed, essentially. Good. Okay, that's an example of Russians fighting. Well, no, it's actually Flambaum is born Russian but lives in Australia now. All right, that's a breakpoint. Questions?
Okay. So you said the laser system will be huge, and it is also 150 nanometers.
This I said,
which is absorbed by oxygen.
Yes.
So everything has to be either in argon or in vacuum. Is that correct?
That is correct. And argon doesn't have the purity, so it has to be in vacuum. It is in vacuum. I will show you a laser system.
Wow. Okay. Thank you.
There's one here. So we're building lasers here that try to do this. I could give an entire talk about just the laser. I could give several entire talks about the laser because it's research on its own. Good. Okay. So now there's all what I told you is essentially historical. Okay. And how do people actually know that there is this low energy transition? Because I can assure you it hasn't been tested or measured until July this year. Okay, so far for the last 40 years, we kind of suspected it. Theoretical nuclear models predicted it, but it was never observed. And there are still people that until a few years ago published papers like, no, the theoretical models are wrong, this state isn't there, okay? So if you look into like databases, Thorium-229, this is the nuclear level structure, okay? These are the excited state. There's no quantum numbers because they would only confuse you. They confuse me. But just to appreciate, these numbers are kilo electron volt transitions, okay? So this is gamma ray energies, photons of very high energy that come from the nucleus. Good. And then you see this, there's this one here, right? They didn't even put a number here because that for nuclear physicists, this is actually zero. It's not an energy. Many of those are actually not really interested in that. They say, well, we can't measure that, so why should we care? Okay, there's a low energy state. Well, only the atomic, the quantum physicists, they love that, but the nuclear physicists, they find it kind of boring. So how do we know about all of these excited states? Well, we as I said, we take uranium-233 and it naturally decays. We just have to wait. And when it decays into those states with a certain probability and then decays down to the ground state under the emission of these energies. And these are characteristic gamma rays, which are used in gamma spectroscopy every day. Like that's kind of what we do here. That's our bread and butter, is finding these energies and identifying, okay, there's uranium. Okay. And now if you look closely at these arrows, you see some of them actually go to the ground state, some of them go to the excited state. Now, if I were able to measure these energies really well, then I could do differences and sums and derive what this little gap here is, right? Okay, let's do that. And that's been done over essentially my age, 40-something years of measuring these energy scales. So whenever somebody has a new nice gamma detector, I don't know why there's this arrow here. It's not on my screen. Anyways, ignore this pointer there. So whenever somebody has a good gamma detector, he or she puts uranium-233 on it and remeasures these values, takes a few sums and differences and publishes a new value of what this one should be. Okay, and that's a story we're playing since many years. And there was a certain time around 2000, this is when I started to develop a certain interest in that, when it was actually 3.5 electron volts. That's right in the visible. That would be so cool, because then we can just take our standard optical laser and play with an atomic nucleus. Turns out that number is too optimistic, too low. Many people published observations of this value. It's many PRLs published. Oh, we've seen it, and then 2 weeks later, there's a paper that says, no, what you see is the radioactivity that produces that hits the nitrogen in the air, and what you see is a nitrogen line and not a thorium line. But still, it's 2 PRL, so it's a way forward to some extent if you want to publish. Okay, so then in 2007. In Berkeley, I think, a group used a spectrometer that was actually supposed to go on a satellite, and it went on a satellite. That is why they only had a very short measuring time. They remeasured this, and they more specifically, they looked at 4 lines. So this is excited states zoomed in on the lower energies here. So these are tens of kilo electron volts, and they measured these 4 decay lines. These are the 4 lines. They measure that as precisely as they can, and they give a new value, which was 7.8 electron volts, which moved it from the optical into the UV range. And as you just pointed out, that means that you can't do it in air, you can't do it in material unless it's UV transparent. Very few materials are. You can't do it in liquid, and many other things. So this new value was kind of disqualifying essentially all of the attempts to observe this nuclear photon before. Okay, that was 2007. Good. Still, let's say so this is still only looking at differences, right? It's still not proving that this thing actually exists. It's an indirect way of determining the energy, but what we really would like to do is to see this photon here, okay? And that's new, that's this year. Good. So we learned a whole lot of stuff. So still within the range of laser, but much harder. I can only underline this. I should put this like blinking. It's really much harder to build a laser in the UV than in the optical. So this is kind of when I started playing with this field. And so the first thing we said is we need to do this better. We need to do this measurement better. And so we set out to build a better detector specifically built for this, not recycle something that was given to us by NASA, but build a dedicated detector. Turns out it takes about 10 years to do this. I will spare you the technical difficulties, but it's a hell of a complicated thing. It's cryogenic. It has everything you want. It has squids. But the basic principle is so stupid that I at least share this with you. So the idea is you have some material that is paramagnetic, and then you apply a magnetic field. So then the spins align. And then if there is a particle that hits it, the temperature changes. And that means the magnetization changes. And they can measure this change of magnetization by a squid. Okay, so it's essentially a bolometer. It's an energy measurement device, and you wouldn't imagine that would be very precise, but it actually is. So this thing has a resolution of few EV at 30 keV. Okay, that's pretty good. Good. So we did, again, as I said, whenever you can, you do a measurement of the uranium-233. That was a very long measurement. It took 8 to 10 years. And then you identify all of these lines. In order to actually get an energy calibration, you have to have like calibration lines. And you say like, yeah, easy. I look up X-ray lines in tables. The problem is if you have the world's best spectrometer, you will have to calibrate it with less good data. Okay. And that is killing us here. So we looked at all of the tables. What can you find? You find all of the materials that are used. You find copper, you find gold, you find whatever, thorium, obviously, you find uranium. Then there's some impurities. All of these lines can be identified. And then you build like a calibration line. It looks beautiful, right? It looks like a really linear detector, really nice. Okay. Then you fit a linear curve to it and you see like, ooh, okay, nice. There's a quadratic part. Okay. We fit the quadratic part, still very nice. But remember, you want to measure electron volt or sub electron volt energies on keV level. That's 10 to the minus 5. and none of the calibrations are at that level. Okay, so that means ultimately we came up with a new value, but with a large systematic error which comes from the calibration, and that is an interesting situation. So whenever now somebody measures one of these calibration lines with a better resolution than it was done in the past, we can actually go back to this data, refit it, and see if that value changes or if we can reduce the systematic error. Okay. Good. So this is 8.10, and this is about why I say approximately 8 EV in the beginning of the presentation. Okay, so that is kind of the best that could be done on gamma spectroscopy, and I think it's not going to get any much better over the next 10 years. I think this approach is kind of maxed out. Okay, good. Questions, guys? Come on. Yeah.
What if the measurement is slightly off and then you build the laser 150 nanometers and that's not
that is anymore? A big risk, and some people have taken this risk. Yeah, no. I will tell you, this is the continuation of the story. But yeah, this is why we said okay. And if you build a laser, it will not be a largely tunable laser. It will be like, because everything is very special. So you cannot say, oh, I'm going to scan over 10 nanometers around 150 nanometer. There's no way. So we really have to narrow down the search range, because as I said, it's a super narrow transition. And finding this over an uncertainty range of 10 nanometers, it takes prohibitively long. It takes maybe, I don't know, 20 years to scan this. So yeah, we need to narrow down, and that's the continuation of the talk. I don't know where to, I don't even know. Well, anyways.
So back to the amount of the thorium-229, are there enough reserves to continuously operate the clock? Or do Vienna have to build its own Manhattan?
Once it's in a crystal, it's there. I mean, it can, okay. It holds just, half of it will be decayed after 8,000 years. So I think that's fine.
Okay. So what if you realize that the crystal you built has to be 1 meter long and has to fulfill a certain concentration, and you don't have enough? What would you do?
Build a better laser.
Oh, okay. All right.
I think it's exactly what's happening. So we're like, there's in German, there's this game Schwarzer Peter. You have the bad card, and so we keep shuffling it between the excitation team and the sample team, which is us. So they always tell you, can you build more thorium? And I say, can you give us more photons? So it's the same thing essentially. All right, good. So now this was about constraining the energy again from indirect measurement, right? So there's this low energy excited state, but we don't directly measure it. We kind of like over a trick try to derive the energy. Okay, now it comes. All this is new. What's coming now? All of this is either unpublished or published. So one of the 3 examples I'm giving is published in May this year. The other stuff isn't published. Good. So just to go back, what did we use here? We used nuclear decay, right? So we took uranium-233. Uranium-233 decays, and in its decay, it populates the excited state of the nucleus. And among those, about 2% go into this state. Okay, so that seems to be a valuable way of producing like excited state thorium, because so far we can't go from the ground state to the excited state because we don't know the energy yet. And but that seems to be a valuable approach. But the problem is this is alpha decay. Alpha decay is a super violent process. So in the alpha decay, a helium core flies out with 5 MeV energy, and for momentum conservation, the remaining daughter nucleus of thorium-229 gets 86 keV back recoil kick. Okay, so this thing is freshly born in its excited state and has a hell of a lot of kinetic energy. It's very difficult to do experiments with this. So if that were in a crystal, and I will show you an example of that, it will actually move from its crystal position through the material and then like lose electrons along the way, scatter, like collect them when it slows down and so on. So all kinds of nasty stuff is happening to this nucleus, which makes spectroscopy or experiments difficult. So somebody thought like, oh, maybe we could use nuclear decay, but not an alpha decay, but a beta decay. Beta decay is really soft. It has an electron that flies away, but because the electron is so light, the recoil is so small that it's almost negligible. So if you use beta decay, then the recoil is a few electron volts. Okay, so it's really less. Okay, you can ignore it. And so there is a way to go to thorium-229 through beta decay, which goes through actinium-229. Problem is actinium lives for about an hour. Okay, so not only it has to be manually produced, you even can't do experiments unless you do them online. You can't have like in your kitchen do something with actinium and then run to the detector, pump it because it needs to go under vacuum and so on. That's not realistic. Okay, needs to be an online experiment. What is a good source for online actinium? Well, CERN. Okay, you go to CERN. CERN at some time uses the proton beam not for collision experiments but for the production of rare isotopes. It's called the Isolde facility. And then if you apply for a project, you can say, please build me an ion beam of actinium-229. We did that. And the experiment is stunningly simple. Okay. Apart from that, you need CERN. Okay. So you take CERN, take that as granted. Out comes an, oh, that's hard to read. Out comes an ion beam. We take this ion beam, we implant this into some UV transparent material under vacuum, of course. UV transparent material, some magnesium fluoride, calcium fluoride, something you buy from Tollabs. You do this for half an hour. Okay, and then you move it in front of a detector physically, like in this case, it's a rotation wheel. You see, this is the ion beam rotation wheel over here. And then you measure the photons that come out. Okay, and when Pete told the guy that came up with this, Piet van Duppen, he's a professor at Leuven University in Belgium, and he said like, oh, we're going to try this. And I said, it's so hopeless. It's never going to work. It worked at first strike. So they did that in the first day of this beamline. They did exactly this, and they measure a photon spectrum. So out comes, this is the wavelength, out comes a peak. This one is a known defect in the host material and calcium fluoride, but this one here, they tried 3 different host materials. This one persists, and we are quite sure that this is actually the photon that is emitted from the excited state of the 229 thorium. Okay, so if I go back right here, it's this one. Okay, so population of excited levels through nuclear decay, not uranium in this case, but actinium, but doesn't really matter. And it's this photon that comes out. And it's a gamma photon because it's from the nucleus, but still kind of optical. Okay, good. And that was published in Nature in May. Cool. Questions? No? Okay. I see I have to speed up a little bit because you should, well, we do the question thing in the talk, okay? Then I can talk more. Okay, good. So and so that's great. So now we have like a source that actually emits the radiation, and we can do spectroscopy on it, and we can probably refine this and so on. So now there's the value here, which is like already in the third digit. Okay, so that's now kind of, if you trust this, which I don't really, because I'm involved in these experiments, I don't trust it entirely. But this is like from this on, you can start building a laser that's sufficiently narrow. Okay, so if you know, okay, on the my error is on the few percent level, then I can start thinking about building a laser. Good. So that's cool, but as I said, you need CERN. So that's not tabletop physics. It's the other end of not being tabletop physics. So we came back trying to use uranium. So we go back to the uranium approach. We take uranium-233, and as I said, we built little crystals. So this is sorry, I should put a scale here. This is 3 millimeters. The diameter of this little thing here is 3 millimeters. So it's a really tiny crystal. We grow this here in-house. It's single crystal, so perfect crystalline order of calcium fluoride. And every now and then a calcium ion is replaced by a thorium ion. That's called doping, okay? That's something we do here. I think we're the only group in Europe that's doping radioactive materials. Good. And so we take this crystal, and as I said, uranium decays to thorium, some of that into the excited state, the low energy excited state that we're looking at, or we're interested in, and then this should further decay to the ground state under the emission of a photon. Okay, so we have to do nothing else but hold this crystal in front of a spectrometer. Okay, and that's significantly smaller than CERN. And if you want, you can see this on Thursday. And but the problem is, as I said, uranium-233 has alpha decay, and that means the state of the freshly born thorium-229 in the crystal is completely unknown. It's been shot through several lattice It probably lost a few electrons along the way, maybe many. So we don't know the chemical state and its position. We don't know the environment. So that means that what I said in the beginning, probably the photon will be transferred to an electronic state and not just be emitted, is very likely. So that means we will probably not see many of these photons, because most of them will go to some, I don't know, some band structure of the crystal. But still, we try and we believe it works. So if we wait for a long time, there is a signal building up, and I can assure you this keeps building up. And we actually also see the VUV photon coming out. Now, there's a discrepancy of about 2 nanometers between what we see here and what we have seen at Leuven, or at the Leuven team and my team being together at Isolde and measuring with this spectrometer. And so it turns out that that these spectrometers, they have to be used very, very carefully, especially when it comes to the calibration. You have to calibrate your system exactly in the same way, meaning the photons go exactly the same way as the source, as the target you want to measure. So what we did in these experiments is we have this little crystal. I have to remember that doesn't work. We have this little crystal. It goes, the light goes on this grating and so on. It's very, like, conceptually very primitive device. And then if we have measured a signal, we take all of this out and we just shine calibration line discharge lamps. We take some nitrogen, some krypton lines, and so on. But we don't use the same illumination techniques. And if we don't, there's a systematic error, and that's we see this in our setup, and I'm pretty sure it's also the case in the Isolde CERN measurement. So we're still sorting out some technical difficulties, but at least there is clear observation of the radiative decay of the first excited nuclear state of thorium-229. Good. Now I'll show you a third one, which comes back to somebody you said about how can we not pump through higher excited state? Who said that? You said that. It's a brilliant idea. Good. You're just not the first to have it, but that's not your fault. Good. Okay. So and we do this at again a larger facility, which is the Spring 8 synchrotron source in Okayama, Japan, which is the largest synchrotron available in this energy range. This energy range being the second excited state of thorium-229, which is at 29 keV. Okay, so we shine excitation light, go to the second excited state. This one goes down, and then we hope to see the VUV signal here. Good. And I will go forward because I'm running out of time. Again, it's a conceptually very primitive system. You take one of our crystals. So these are actually crystals from Vienna that are used there. So we ship them. There are crystals. They hold them into their synchrotron about, I don't know, 10 minutes, half an hour. They expose them to X-ray light, super violent thing, right? This thing glows like blue, horrible. There's a whole lot of stuff. If you shine in an intense 30 keV source on a solid state target, there's a lot of stuff happening. Not all of it related to thorium nucleus. So, and they do this for half an hour, then they physically move the crystal in front of a detector, and that's essentially a PMT that is counting photons. There's some filter optics, but that's technicalities. I don't bother you with that. Okay, but that also works. So if they scan the wavelength of the excitation source to the second excited state, there's a nice peak here, which means that you see photons coming out the moment you hit the second excited state, and then it falls down and it falls down and it sends out a X-ray and a photon. Okay, and this is the detection of the photon when scanning the energy. Wow, that's a positive reaction. Okay, good. So we see the photon coming out when we scan the excitation to the second excited state, and that's the lifetime. Okay, so that's the if we go to the peak, we shine in our X-ray, we move it to the detector, and we just wait. Yeah, and you see it's 600 seconds. So first excited state lives for 600 seconds in a solid state environment. So that's, if you consider this in terms of line width, could be good. All right, good. And that kind of brings me to the end of where we are. So all of this is very new and very preliminary, but it says since the beginning of this year, we see the photon coming out of the lowest energy excited state of all nuclei, which is cool. And the obvious next step is the direct excitation, which brings us to the question of a laser system. And yes, we have a laser system. It was built by a German group, Eckhard Pike's group at PTB, Physikalisch-Technische Bundesanstalt. And so I spare you details, but it's like a huge laser system which uses high harmonic frequency, sum doubling, and so on and so on and so on. So it fills an entire table. It took 3 years to build, but it produces 150 nanometer light, okay, with a line width of about 1 gigahertz. So it's not a very narrow line width. There's actually, it's very, very difficult to have not only photons at 150 nanometers, but also have them narrow line width. Good. So this is a picture. You see all kinds of lasers, and then they shoot on, again, a little crystal coming from Vienna. So here you see, again, 3 millimeter. We have these crystals. They have they are cylindrical shape, 3 millimeters in diameter, and we cut them into little pucks, polish them on both sides. They become an optics element, and are held inside a vacuum system. Okay, so you see there's a vacuum holder, there's a collection mirror, and so on and so on. And then you see we scan, we try to excite, we shoot the laser, we see photons come out. We don't see photons. We move the wavelength of the laser. We scan, we scan, we scan, we scan, and we already scanned since 3 months without success. The reason for this is probably technical. So there's all kinds of nasty stuff. If you shine in UV light, again, this is UV light. This is not even X-ray, but still UV light on a crystal produces all kinds of damage in the material on the surfaces. We have to find ways to mitigate this. One of them is that we have to cryogenically cool this crystal, which is nice because then the crystal doesn't get damaged. But over time, there's some kind of like a layer forming. It's essentially water or ice forming on the crystal. And if you see these photon yields going down, so that's 1 day of measurement. And you see the photon yield goes down just because there's an ice layer, and then people go to sleep. They turn off the cooling. Next morning, it's here. They scan for another day. They scan for another day. They scan for another day, and so on. Okay, so that's a very, very, very tedious operation. But at some point, we will succeed. And that's what's currently ongoing. And if that works, then we would have the first time a nuclear excited state that is controlled by a laser. And I think that would be cool. Good. And that brings me to the end of this presentation. And I shouldn't finish without giving credits, because I show a whole lot of stuff, but that's obviously done by a whole lot of people also. And there's a lot of technology development, and you see there's gamma detection, there's laser development, there's work at CERN, there's work at Japan. So there's many teams. It's a lot of collaborative work. And so you don't have to read these names, but please appreciate the fact that that wouldn't be possible if only my team here in Vienna would be doing this, but this is a almost global effort. All right, now I'm really done.
Are there other questions that you haven't asked?
So I guess there's a lot of sort of innovation that you're forced to do. Are there any spin-outs in sort of other technologies that
Yeah.
come
So
to the result?
we're currently we're patenting something. It's first time for me. It's a mixed experience. Some parts are cool, some parts are really tedious. But there are. So we have a collaboration with Toptica in the development of UV lasers. We have as I said, we're patenting something that is more in the NMR NQR range. But as you said, so there's continuously development of technology that goes beyond like commercially available stuff. Most of the time we do it together with the company. So the spectrometer you've seen for the uranium experiment was like to develop together with the company. And yeah, we can't do this. There's so much technology, we need the help of companies.